Okay, welcome back. This is Mr. Hassan's Maths channel, and this is a question number 11 from my end of topic worksheet for integration, P1. This is from the Cambridge CAIE 9709 International A-Level. And this is a question here about volumes of revolution, which is similar to the question 10, which you'll also find in the playlist, which will appear over here. Okay, for this particular worksheet. Now, this question number 11, again, is one of those questions that I have modified from some other type of question, and I've made some changes to the equations as well, so that it's something that will be relevant to what we're doing in P1 in Cambridge. There's not that many questions involving the volumes of revolution between two curves, so that's why I've kind of taken this question, so that the actual past paper questions that you'll find, you won't have done them before. You can practice them, from scratch, which is better for you when you're trying to practice for your real exam. So this is an example from another, type of question which I've adapted to make it into this. So first of all, it says the diagram shows the curves y equals x squared plus 1 and y equals, in brackets, 2x minus 1 to the power of 4. Okay, and it says the shaded region is bounded by the two curves and the line x equals a half. Find the volume of revolution of the solid produced when the shaded region is rotated completely. And here we're going to do about the x-axis and then about the y-axis. So we're going to start off, let's start with the x-axis. We're going to deal with this part first. So we've got to basically take this shaded area here and rotate it around the x-axis. So you can see there's going to be a part here where there's going to be a gap in the the shape, in the volume that we're going the solid that we're going to get when we rotate this. Okay, so the way to deal with such a question, or one way of dealing with such a question, is to think of like a small rectangular part. Make it a bit thinner than that. A small rectangular part of the section, just consider it a really thin rectangle, and that part is going to be rotated around the x-axis. Okay, now if you take that area and rotate it around the x-axis, and you're looking from this angle over here, what you'll see in front of you is you'll see basically some sort of a shape like this, like a circle with a hole in it. If you're looking from that side, if you're looking, you'll see it has a depth because it's got slight thickness. So you're going to have something like this. It's going to be some sort of a cylinder with a hole in it. Okay, this part will be the whole part. Okay, and that will be the shaded part there would be the actual volume or the solid that's there. Okay, and you'll have this hole in the middle. Okay, so it'll be something like this. Now, to find the volume of this solid, this cylinder, this one little cylinder that's going to be formed when this goes all the way around the x-axis, to find the volume of that cylinder, you've got to find basically the area of this cross section, which is this area here, times by how deep or how thick the cylinder is, which would be like its thickness. Okay, so in this case, you're going to have like the outer radius and the inner radius. Okay, so you're going to find the volume and say this is the thickness, we call it h, this is big R, and this is small r. Okay, let me change the color so it's clearer. So this is h, this is big R, and this is small r. So the volume is going to be, we know the volume of a cylinder is pi times r squared h. So in this case, you're going to have the big cylinder, pi capital r squared h, minus the volume of the small cylinder, which is pi times small r squared h, which gives you pi times r big R squared minus small r squared times h. That will give you the volume of the shape with the hole inside, like a donut shape or a tire shape. Okay, that's the volume of that shape there. So if we relate it to our diagram here, it's like the outer radius is the y value on the curve that's on top. Okay, it's the y value of the curve on top. And the smaller radius is like the y value of the curve underneath. Okay, so if we call this like y1 and call this y2, then we can say the volume of our shape here, when you revolve it around the x-axis, is going to be pi times and you'll have y1 squared minus y2 squared times h. And h is going to be basically the thickness of this, which is a little amount along the x-axis, which we call dx. Okay, it's going to be dx. So the h is going to be actually dx. Okay, so that's the volume of that one little cylinder there. And we want to find all the cylinders between 0 and a half. So what we're going to do is we're going to integrate this between the 2 points that we want to find the volume of revolution, where the two limits are. Okay, so this is a formula that will help us find the volume of revolution between two curves around the x-axis. Okay, so the y1 stands for the equation of the curve that's higher up, and y2 for the one that's lower down, and we carry out this. So in this case, I'm going to write the pi on the outside. I have my limits are between 0 and a half, and I have my first equation, which is x squared plus 1. So I have x squared plus 1, and that's going to be squared, minus the second equation, which is 2x minus 1 to the power 4, but that has to all be squared, and that's going to be all integrated with respect to x. So that's pi y1 squared minus y2 squared dx. That will tell me the volume of the shaded region when it revolves around the x-axis. So how do I now go on to integrate this? Well, the first part here, I have to expand this bracket, because what's inside the function, if I differentiate it, I'm going to get 2x. Outside of this function there's no x term. So therefore, I see that this is not the result of the chain rule. So I cannot reverse the chain rule. If I had something like an x term outside the bracket, then I could use reversing the chain rule. But there's no x term outside the bracket multiplying it, so I can't. So I have to expand this, which is not too difficult. It's only up to x squared. So you have pi 0 to a half. Now this is going to give me, if I square this, I'm going to square the first term, that'll be x to the power 4. Then I'm going to multiply these together and double that, so it's going to be plus 2x squared. And then I'm going to square the last term, which is going to be 1, then take away. Now this is going to give me 2x minus 1 to the power of 8. Okay, which if I wanted to expand that to solve would take you a long time. All right, to the power of 8, you'll have to use binomial expansion or a lot of terms or whatever. But we can see here that in this case, I can use reversing the chain rule. Why? Because if I differentiate 2x minus 1, I get a constant. And what's multiplying this bracket is also a constant. So it's of the form of something which you can recognize as the reverse of the chain rule. The chain rule can be reversed. This is the result of the chain rule having been applied. Think about if you differentiate something to get this, you can reverse the chain rule to integrate this. So that's that part. I can do that. So these terms now are easy to integrate as normal, and this I can use the reverse of the chain rule. So that's what I'm going to do now. Once I start integrating, do not write the integral sign anymore. Now we're going to have our square brackets, no integral sign. So we have x to the power 4 divided by, add 1 to the power and then divide by the new power. So x to the power 5 divided by 5 plus 2x to the power 3 divided by 3 plus x. And then to reverse the chain rule here, you're going to add 1 to the power. So you leave it as it is, but you just add 1 to the power. Then you divide by the new power, and also you divide by the differential of what's inside the function. If you differentiate 2x minus 1, you get 2. So you multiply the denominator by 2. So you're dividing by the new power and also dividing by the differential of what's inside the function. Of course, this is a definite integral. We don't need to put plus c. So we have our limits 0 and a half. And now we are ready to substitute these values in and find our volume. So we have v equals pi times, don't forget the pi. Now I'm going to put a half into here first, and then I'm going to put 0 into here. So a half to the power of 5 is 1 over 32. And so 1 over 32 divided by 5 is 1 over 160. Plus 2 times 1 over 8 cubed. Now 1 over 8 cubed, so 1 over 2 cubed is 1 over 8. So 2 times 1 over 8 is 1 over 4 divided by 3 is 1 over 12. Plus, just x is a half. Minus, now when I put a half into here, I'll have 2 times a half, which is 1, minus 1, which is 0. So this is going to become 0. But then I've got to take away what I get when I put 1 into here. Now you might think that putting 1 into here Okay, so what 0 into here will just give us 0 for everything. Well, it does for these three, 0 and 0 and 0. For this, if I put 0 in this, I end up with a minus, and then this becomes, there's a minus in front of it, remember? Put 0 into here, that becomes minus 1 over 1 minus 1 to the power of 9, which is minus 1 over 9 times 2 is 18. If you do minus 1, if you put 0 into here, that becomes 0. You have minus 1 to the power of 9. If you raise a negative number to an odd power, it stays negative. So the minus 1 to the power of 9 becomes minus 9 over 18. And that's that part done. And close that bracket. So let's work out what we get. This is going to be basically 1 over 60 plus 1 over 12 plus a half. And then you're going to have minus, well, inside here you're going to get a positive. So you'll have to take away 1 over 18. Okay, so let's write this out a bit. It's a bit confusing the way it looks like now. Let's just simplify it. So this is 1 over 160 plus 1 over 12 plus half. That's a 0. So I'm going to have a minus, and then that's going to give me a plus. So it's minus 1 over 18. Okay, minus 1 over 18. Okay, so I've got to add these together and take away that. So let's do that. We've got 1 over 160 plus 1 over 12, and then you got plus a half, and then this would be minus 1 over 18, and that gives us 769 over 1440. So we have 769 over 1440, and don't forget the pi. Okay, it's times pi. Okay, so that's units cubed. I don't know if it's going to be, I shouldn't put centimeters. I started putting centimeters. So units cubed. And there's the answer to this question. That's part A, okay, where you find the volume around the x-axis between these two curves. All right, now we're going to go on to part B. Part B now. Now, part B, it says find the volume around the y-axis. The volume formed when this whole shaded region is wrapped around the y-axis. Now, in this case, we have the issue here that there's one function and there's the line x equals a half, and there's another separate function and the line x equals a half. So we've got to split this into two separate parts because there's two separate functions here, okay, which they meet at this point here. And we can see that that point is going to be, if that's y equals x squared plus 1, that's where they both cross the x-axis when y equals 0. Sorry, when x is 0. So when we can see when x is 0, this is going to be 1, right? X is 0, this is 1, x is 0, this is also going to be minus 1 to the power 4, which is 1. So they meet at that point, and that is where we have to divide this into two separate parts. Okay, I can't use one equation for both of them because the equations change in between these regions. And I've got to think about this region here when I revolve it around the x-axis, the y-axis this time. Okay, I've got to think about, it's going to be basically this part here revolving around. So it's going to be like the outside of this. It's like a rectangle. It's like a cuboid with a bowl cut out of it. Okay, it's that kind of shape. Okay, so it's the outside of that bowl as it goes around. So we could tackle this in a couple of ways. We could have the whole cylinder, this whole cylinder, take away the area between the volume between the curve and the y-axis. As you take that away from the whole cylinder, we could do that. Or we could just find the volume between this line, x equals a half, and this curve, but the curve has to be expressed as x equals. So it'll be x squared equals y minus 1. And in fact, that form will help us actually for what we have to do here. So I'm going to leave it like that. And this one, you're going to have to deal with this side. And that's going to be, you have to make x a subject. So I'll do that in a minute, but I'll explain that part in a minute. Let's just deal with the first one here. So again, we're going to have the basic idea that when you find the volume of something that's wrapping around the y-axis, you have pi times x squared dy. Okay, because now your x is like the radius, and your dy is like the kind of height of the cylinder. Okay, so that's kind of switches around. Instead of y squared dx, it's x squared dy. So that's why we have to express these in terms of, x instead of y. Now, as I mentioned, we could do this in two ways. I'm going to do it the way where we just do it in one go. I'll take the equation of, like I'll take the outer radius, which will be that, and the inner radius, which will be this. So the outer radius would be like y1 here, and the inner radius would be y2. So what I'll do here is I'll say that the volume is equal to pi times the integral between the 2 points that we are going to take as our limits of, and we'll have, instead of y, have x1 squared minus x2 squared dy. Okay, so I need the equations in terms of x. So in the first one, this is x equals a half. That's fine. So you have v equals pi. I'm going to have x equals a half, so it's going to be a half squared minus and x2 squared. Now x2 is y minus, x2 squared is y minus 1. So I can just put minus y minus 1. That is x squared. Okay, that is x2 squared. And that's integrated with respect to y between the limits of, well, we said this part is 1. We're going to find what that limit is. That limit up there is where this curve, x equals a half, meets this curve. So when x equals a half, y equals a half squared plus 1, which is a quarter plus 1, which is 5 over 4, 1.25. So that's the point, 1.25. So that's going to be the upper limit. I'll put 5 over 4 as a fraction. I think fractions are easy to do with here. So that's 5 over 4. Okay, so that will give me the volume of that that part over there. Around, you wrap it around the x-axis. And then the volume of part 2, I'll deal with that afterwards. Let's deal with this first. So let's find what this is first. So I've got to find this integral. So I have the volume of the first part is pi. You have the limits 1 and 5 over 4. And now you're going to have, that's a quarter, minus 1, that's plus 1, that's 5 over 4, minus y, integrated with respect to x. Okay, all right, that's getting somewhere. So now I can actually integrate this. So I have 5 over 4 y minus y squared over 2. You add this one gains the y, and this one becomes, add 1 to the power divided by the new power, and we have our limits of 5 over 4 and 1. So let's put those limits in and find the volume. So you have, don't forget the pi always. You have 5 over 4. If you put 5 over 4 inside the y, that gives you 25 over 16 minus, and if you do 5 over 4 squared, you get 25 over 16, but over 2, so it's 25 over 32. Okay, and don't forget you got to put 1 in as well. Now when you put 1 instead of y, that gives you 5 over 4. And you put 1 instead of y, again you get minus a half. Okay, because 1 squared is 1. All right, so now that should give us our answer. So we can just stick that in the calculator and get it. So we have 25 over 16 minus 25 over 32. Okay, then you're going to have minus, I'll just do it as it is, 5 over 4 minus a half. And what does that give us? 1 over 32. So we got pi over 32 units cubed. That's the volume of that first part. So we haven't finished. We've got to now find the volume of the second part, which is this section over here. All right, so for this section over here, we got to be a bit careful because as you can see, when I try to make x a subject, I've got to take the fourth root of both sides. So I'm going to have y to the power of a quarter equals 2x minus 1. However, we know we can have either the positive or negative fourth root, just like square root. And we can see here that we're on the left of the vertex, just like with quadratics, you see the left of the vertex, that would be the part which would be considered as, if you're thinking in terms of the x, the negative square root part. Okay, so I'm going to put here the negative square root part of x, of y, sorry. That's a negative square root, the fourth root. All right, so that makes a difference here. And now I can make x a subject. So if I add 1 to both sides, I have 1 minus y to the power of a quarter equals 2x. So I can say x is equal to 1 minus y to the power of a quarter divided by 2. So that's the equation of this line or this curve in terms of x, which is what I need. So the volume of part 2 is going to be pi times, and as we said, it's x1 squared minus x2 squared let me just put this in proper notation. The integral of x1 squared minus x2 squared dy. Okay, so I need x in terms of y for both of them. In terms of the first equation, that's going to be x equals a half. So that's going to be pi times, that's going to be a half squared minus, and then I'm going to have this, which is 1 minus y to the power of a quarter over 2 all squared. All of that integrated with respect to y between the limits of, now this is the limits of 0, if we're rotating it this way, 0 and 1. Between the limits of 0 and 1. Okay, so that's what we need to work out. So let's get it a bit more friendly here. So you have pi times the integral of, that's going to be a quarter, minus, and you're going to have another, let's take this half out, it'll be half squared out, so that'll be minus a quarter times, and I have 1 minus y to the power of a quarter squared, and that's integrated with respect to y. So what I can do here is actually take out this whole thing, this whole quarter thing. So we have pi over 4 times the integral of, and this is 1 minus, and now what I'm going to do is I'm going to actually expand this part, because I can see I cannot reverse the chain rule again, because the differential of y to the power of a quarter is going to be a quarter y to the power of minus 3/4, which outside you don't have anything like that. So I have to square this bracket to make them into separate terms, such that I can then integrate them. So if I square this bracket, I'll have 1, and then I'll have these two multiplied and doubled, so minus 2 times y to the power of a quarter, and then I'll have minus y to the power of a quarter squared, which is going to be where you multiply the power by 2, okay, because when you raise something to a power, you multiply those powers, so it's going to be 2 times a quarter, which is a half, and it's going to be positive, because you're squaring, so it'll be positive y to the power of a half, and that's what I have to integrate with respect to y between the limits of 1 and 0 and 1. Between 0 and 1. Okay, so we're almost there. Let's see if we can fit it in here. Maybe I'll have to go to the next page. So you're going to have pi times, now if I get this ready still, I have 1 minus 1, which is 0. So I'm left with minus 1 times 2 y to the power of a quarter, which is positive 2y to the power of a quarter, and then minus 1 times plus, so it's minus y to the power of a half, and that has to be integrated with respect to y. Now I can integrate between the limits of 0 and 1, of course. I can integrate this. I add 1 to the power, so I have 2y. If I add 1 to a quarter, I get 5 over 4. Then I have to divide by 5 over 4. Minus y, if I add 1 to the power, I get 3 over 2. So I have to divide by 3 over 2. So if I divide by 3 over 2, it's like multiplying by 2/3. And I have my limits of 0 and 1. So let me just simplify this. 5 over 4. 2 divided by 5 over 4 is like 2 times 4 over 5, which is 8 over 5. Y to the power of 5 over 4 minus 2/3 y to the power of 3 over 2 between 0 and 1. Okay, so we're almost there. We have to just now put 1 in here and then 0 in here. So I'll just fit it in the bottom here. Okay. In fact, I'll take you to the next page. That's probably better. So 8 over 5 y to the power of 5 over 4 minus 2/3 y to the power of 3 over 2. Okay, so I've still got this stuff here. No problem. So we're in the middle of doing this question. So we had 8 over 5 y to the power of 5 over 4 minus 2/3 y to the power of 3 over 2, 0 and 1. And we had the volume of part 1 of the first section was pi over 32 units cubed. Let me just make sure of that. Yeah, okay, so now we can continue. All we have to do is substitute 1, so this is the volume of part 2. So put 1 into here. Of course, 1 raised to any power is going to be 1. That'll be 8 over 5 minus, I forgot something here. There was a pi over 4 on the outside. Don't forget the pi. Let me make sure I wrote it there. That went missing. That's a pi over 4 from here, a pi over 4 there, and a pi over 4 there. Okay, be very careful. Don't forget about the pi's. Okay, so there's a pi over 4 there, which I forgot about for a second. So that's pi over 4, 8/5 minus 2/3. Okay, so you have pi over 4. Now, 15 will be your common denominator. That's going to be 24 minus 10, which is 14 over 15. That counts with that, leaves you 7 and 2. So you end up with 7 over 30 pi. So now that's volume 1. So the total volume is volume 1 plus volume 2, which is pi over 32 plus 7 pi over 30. So I'll just do that in a calculator, no problem. So we have pi over 32, so I'll just do it as 1 over 32 plus 7 over 30, which gives us 127 over 480, 127 over 480 pi units cubed. And there's the answer. Okay, so that's quite long-winded, but as I said, I invented this question, so it might most probably won't be so complicated, but it's well within our syllabus. And there would be an alternative way of answering this question, but you'd still have to split it into two parts. You could have the whole cylinder minus the volume of what's between here and there. So you could the whole cylinder would be all the way up to here, which would have been the radius would have been 1/2, and the height would be between 1 and 1.25. So it would have been a quarter. The height would have been a quarter. So you'd have had a cylinder like this. That would have been 1/2, and the height would have been a quarter. Okay, so you'd have had pi times, you would have had the radius squared, which is 1/2 squared, times the height, which would have been a quarter. And that would have been the volume of the whole cylinder. And then you would have had to take away the volume of this curve, okay, as it's rotated around the y-axis between 1 and 1.25. And that would have, when you've subtracted those two volumes, you would have got this answer, pi over 32. Okay, so whichever way you want to do it, that's fine. And you could have done a similar thing for this. Found the volume of the cylinder between 0 and 1. Okay, and the radius would have been 1. 1/2, sorry, and then taken away from that the volume of this curve as it's rotated around the y-axis between 0 and 1, and that would have given you the same volume. Added them together and you get the answer. All right, so as I said, other questions from this particular worksheet, if I've answered them, will be in the playlist that will appear. It's linked over here. Other questions from integration from P1 of Edexcel, of Cambridge. The Cambridge syllabus will be found in this playlist over here. This is for the A-level P1 9709 syllabus. Other questions dealing with integration in general can be found in this playlist, and you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.